Hi guys, welcome back to the Astro Imaging channel. Today's topic is on CCD cameras, SNR, the signal-to-noise ratio, and the math behind it. It's a really interesting topic, and it's going to be presented by myself and Josh Smith, and I think it's going to be an exciting topic, but I'm going to qualify this in advance. If anybody thinks we got it wrong, feel free to chime in. We're gonna at the end we're gonna have a Q&A, and I think the discussion in the Q&A might be really interesting and might actually be one of the most interesting parts of this. But until we get to that, I'm gonna switch right over to my PowerPoint presentation. And you guys remember, no need to really drop out today, because I think we. Anybody that's outside or anybody that's viewing this from YouTube can just type in Q&A. That should be activated. It looks like it is. And you guys can chat amongst yourselves in chat down here, and we'll try and get to that. But I'm going to switch right over to, let's see, I have to go full screen. There's the crazy screen. My excuse me. My PowerPoint, and we're in. Can you, if you guys can't see my full screen PowerPoint presentation, just please tell me now. If you can see it, I'm just going to go right ahead. And remember, keep your microphones off if you're not speaking, because we can't tell where the sounds are coming from, so it's hard for us to mute you. And if you have to speak, just unmute your microphone. All right, tonight's topic is on CCDs, SNR, and the math. In advance, I want to thank a few people: John Rista, David Alt, Jim Counterweight. It was nice having them jump in there, because everyone kind of contributed a bit, and I think tried to keep me out of trouble. And we have, I think, a couple of these people are here, and they'll keep us honest, so to speak. Tonight, in regards to the hardware, we're just going to go over the fundamentals of the CCD, basically how it works, and the hopes are that you'll be able to follow the process pretty much from the first photon to the final image, and that really gives you a good idea as to what we're doing. In regards to the math, we want to give you a good understanding of it, but only a good enough understanding of it that you'll know where it's applicable and how we use it to make our images better. You don't need to be a mathematician. I'm not a mathematician, but you may have to trust a mathematician. You may have to say, well, okay, this does work this way. Well, yes, it does. Okay, well, what are the ramifications of that? And we'll take that and kind of see where we can go with it. So it's an intimidating topic. So the first thing I'm going to do is I'm going to help you out. Does that help you out? I hope so. Tough telling jokes in a webcast. You don't hear anyone laugh, and they probably aren't laughing to begin with, but oh well. If you saw the forum post on Cloudy Nights, I tried to take a more complex equation for signal-to-noise ratio and simplify it. And I thought I had it. I thought I had it right. Actually, I knew I made one mistake, and I came driving home from work to correct the mistake, and I saw John Rista posted and told me to correct the mistake, politely posted, and pointed it out. I knew where the mistake was, so I corrected it, and John looked at it and he said, "Oh, it looks good, but it's still wrong." And it's funny, it was still wrong, and I knew why I made the first mistake. The first mistake was really just a please excuse my dear Aunt Sally mistake, for lack of a better words. But the second mistake was more interesting, and I'm going to get into what the second mistake was. But first, let's jump right into this equation. It is a big, intimidating piece of math, and I told you I got stuck with please excuse my dear Aunt Sally. In fact, if you look at the end of this equation at the denominator, read noise squared, I had that squared in the wrong place, and it messed it up. It didn't add up. The other issue I had, which was actually kind of a bigger issue, but something of interest to me, is if you notice target signal, it's in the numerator and the denominator. If you look at the target signal in the denominator at the bottom, I actually wanted to use photon noise there. And I'll explain what photon noise is, but I posted it in my equation, and they pretty much said, oh yeah, but you can't use that. And I listened to what they were saying, and I looked at the equation, and it wasn't until I listened to what they were saying and I looked at the equation that I really understood what they were saying. So I guess what I'm saying is they had a good reason to not let me use it, and I really had to look at it to understand it. But just based on this slide, you're going to see a few keywords or variables. Target signal, n subs, simple enough, number of subs. At the bottom, target signal, dark current, read noise. What are those? And we're going to go right into them. Starting with target signal. Target signal is basically what we want. Target signal is photons coming from our target. Actually, photons coming from both our target and the background. And you have to remember that, because one of the issues we're going to get into, really it does take place in the background. It takes place in the dimmest areas of our images. And that's where we have issues. We want the dim spots of our images to appear clear, but there are certain things that prevent it from happening, or there are certain hoops you have to jump through to get a clear target background. More advanced equations than the one I showed you. In fact, the one that I simplified it from actually does take the foreground signal and the background signal separately, and it allows you to extrapolate a few additional things from it. In fact, it's a better equation, but I wanted to simplify it, and I think I simplified it enough that I'll be able to make this. But with target signal, there are a few exceptions to the rule. It's the foreground signal, it's the background signal. Light pollution is one of those exceptions, because light pollution just comes in with the target signal. Your camera can't distinguish between light pollution and target signal. It just comes in, it gets integrated. The other exception is photon noise, and that's one of the cool things. And I'm going to show you that, but I told you before, they wouldn't let me use photon noise in that equation. And there's a reason, because photon noise is part of the target signal. And it's kind of integrated into the target signal. I use that word liberally, but it's part of the target signal. It's actually a specific part of the target signal. But for all our purposes, target signal is relatively simple. Signal, you double the exposure, doubling the exposures doubles the signal. It's that simple. And we measure the signal, whether it comes from the foreground or background, in photons per pixel per second. And keep in mind, in this ring nebula, the photons per pixel per second in the area of the ring is going to be greater than that of the background. And that is basically target signal. Target signal, I think, is relatively easy to understand. Photon noise. Now, I love photon noise. Photon noise, to me, is one of the coolest things. Photon noise really demonstrates the odd behavior of light. You've probably heard of the particle-wave duality, and this is where you get into really cool things. Light behaves as both a particle and a wave. Well, photon noise demonstrates the particle aspect of light. Photons are discrete. You can count them, and that's good, because that's exactly what we're doing. But the other good thing about photon noise is that it's random and predictable. When I say random, it doesn't develop into any pattern. It just requires that you get a good sampling of the signal. So when I say it's random, random is a good thing in this when it comes to noise, because it averages out. When I say it's predictable, it's mathematically predictable, so we know how to take it into account. You can't overcome read noise mathematically, but you can know exactly how long you have to expose to overcome read noise. It's just very predictable. The other thing I like about, or excuse me, I said read noise, I meant photon noise. And I don't know how many times I repeated that, but I meant photon noise. My apologies for that. The other great thing about photon noise is that there's nothing wrong with your camera. Buying a better camera isn't going to fix photon noise. this slide is not going to cost you any more money. You can't spend your way out of photon noise. Well, maybe you can. Aperture, I guess aperture will get you more integration faster. So maybe this slide will cost you money, but when it comes to camera, you're not going to spend more money on your camera to get better behavior out of the photon noise. Photon noise is measured in photons per pixel per second, and there's a good fix for it. More integration time. Is that a good fix for it? I don't know. But at the same time, that more integration time can come in two different ways: more subs or longer subs. There's a distinction, and I didn't make that distinction in my equation above, but there is a distinction. Moving on, the next type of noise that we typically see is dark current. And dark current comes from low-level circuit current within the CCD camera. I'm going to get into a little bit about how it works, and I'll tell you where exactly the dark current gets applied or introduced. But I like to think of it as stray electrons. There's a charged field happening in your camera, and it's just hard to keep it under control. Perfect manufacturing processes are intended to keep it under control, but nothing's perfect because we live in the real world. One of the good things about dark current, though, is it can be limited by lowering the temperature, and it actually fits the temperature curve nicely, and it's very predictable when it comes to temperature. In fact, it doubles for every 5 to 6 degree rise in temperature, but more importantly, it halves for every 5 to 6 degree drop in temperature. So we end up cooling our cameras to 10 below or 20 below, pretty much as low as we can get them so that the dark current won't be a factor for us. The dark current is also predictable in that it's the noise equals the square root of the dark current. I think I got that one right. I might have to check on that, and I apologize. If I did get anything wrong, write them down and correct me. At the same time, dark current is measured in electrons per pixel per sec. And you notice that read noise and target signal were photons per pixel per sec, but remember, dark current is coming from the camera. The target signal and the photon noise is not coming from the camera. Are you guys still there? I'm sorry, I'm going to ask you to chime back in if you're still there, because I just heard a noise.
We are here.
Okay, I'm sorry for that. I heard a noise that I thought got me cut out. Yeah, so you'll notice the distinction. Since this comes from your camera, it's more appropriately measured in electrons per pixel per sec, whereas photon noise and target signal were measured more by the photons per pixel per sec. In reality, it doesn't matter because you can convert easily between the two, but that's something we may or may not get into in the next few slides. But the fix for dark current is cooling your camera sensor. Primary fix. You can cool your camera sensor pretty much till dark current becomes irrelevant. And we all cool our camera sensors when we have CCDs. Not all of us, but that's the one big thing that you take into account when getting a CCD. Regulated cooling makes everything a lot easier. The other fix for dark current is taking dark frames, and what dark frames do is they help build the pedestal. The dark current just adds a pedestal of current to your exposures, and dark frames average do a pretty good job of setting that pedestal and kind of defining it for further removal. This slide could cost you money. Better cameras will have lower dark current. They do certain things within cameras to keep the dark current low. Sometimes it affects the other factors, sometimes it doesn't, but this slide will cost you money because a better camera will have lower dark current. Read noise. I don't like read noise. As I was discussing with the guys doing the presentation and the guys on cloudy nights, I wonder whether I overstate the issue with read noise, but I don't think I do. And I'll explain what I mean by that. But first of all, read noise comes from the circuitry within the camera. It comes from sources that could be on the CCD or excuse me, that are on the chip or off the chip. The amplifier and the ADC, I believe, are considered off chip, and a lot of read noise comes from them. Some of the read noise could come from the chip itself. In general, CCD manufacturers combine all of the on-chip noise that's not dark current and consider it read noise. That noise can be random or can have a pattern. It'll either be random or periodic noise. The pattern can show up as hot pixels or banding, and patterns are very, very bad when it comes to CCDs. Patterns integrate. Periodic noise integrates along with your signal. When we go back to the SNR, I'll show you a little bit of how that shows up. But I think read noise really is the bane of astro imagers. Now, I say that as someone who right now is taking 30-minute exposures in O3 and saying that's not quite enough for me. I notice that the longer I expose these really narrow band filters, the deeper I go and the more noise-free it appears in the final stacked image. Now I'm willing to push my overall integration times up to 12, 13 hours for a single channel. That means I'm probably at the same time wanting to push my individual sub-exposure times up to 40 minutes to an hour. A lot of the guys on cloudy nights are having a lot of success. And why is that? You're separating the signal from that read noise. But at the same time, where I'm doing it on that end, newcomers are coming in, and they're trying to expose in 5-second exposures. I saw on another forum, not on Cloudy Nights, but another forum, someone shot Andromeda, 5-second exposures. And I said, you want to push that up. You want to push that exposure time up in any way you can. He was on a fixed tripod, so it was just a matter of seconds. But read noise ultimately limits myself at 40 minutes and this guy on the forum at 5 seconds. And read noise is the ultimate limitation. If it wasn't for read noise, if you could take enough 5-second exposures, it would equal the same 40-minute exposures at the same time. But read noise is that limitation. And that's why I really hate read noise. Read noise is measured in electrons per pixel RMS, so it's actually like a kind of a standard deviation. It's how far from the mean on average are you going to find that at a pixel level are you going to find that error to be. And read noise coming from the camera really, I'll show you another place it's limiting. But the fix for read noise, and I can't elaborate or exaggerate this enough. I can't emphasize this enough. The fix for read noise is bias frames, and in my next couple slides, I'm going to tell you a couple ways where that's important. But the other fix is longer subs. So on one end, you want bias frames to remove that pattern. On the other end, you want longer subs to expose, so your histogram separates from the left side and escapes that read noise bias pattern. It's tough with narrowband. It's also tough if you're limited to very, very short subs. I'll kind of show you a little bit of how that plays out in one particular step of the process. But for now, we go back to the signal-to-noise ratio, and I hope, I haven't explained much in mathematics. I haven't really gone much in depth of mathematics. I probably can't go in depth of mathematics because that's where my knowledge is limited. But what I can extrapolate from it kind of makes sense. All of a sudden, you know pretty well what each variable is. You know that you see that the target signal and the dark current are pretty much, it's the square root of them. The target signal that's on the bottom there represents the photon noise, and the dark current on the bottom there represents the dark current, of course. And there's the square root of that, the number of subs times each and the square root taken of that. But the read noise is squared, and that's where it becomes kind of pesky. That's where it becomes persistent. And you'll see how that plays out in future graphs. You don't have to understand this. You don't have to mathematically prove this. People have done this in the past. But if you look at what it says, you can take a few things away from it. And I just put there at the bottom the takeaways. Photon noise. What can you do? More overall integration time. It's the only fix for it. Dark current. Cooling and calibration. And read noise. longer subs, and calibration. Those are the main takeaways. And the way I look at it, we're astro imagers. We do everything to get the best out of our images. So let's hit it with the kitchen sink strategy. Let's do all of them. Lots of integration time. Let's cool well. Let's make sure we do calibration. Let's use all of our calibration frames. Let's make sure our subs are sufficiently long. And at the same time, calibration, let's do it right. Having gone over this, having, I think, given you a little bit better understanding of the SNR ratio, I think the calibration is actually going to be pretty easy. And I'm just going to jump into the calibration math. Calibration frames, I put lights up there, but lights aren't your calibration frames. Lights get calibrated. Your calibration frames are your darks, your bias, and your flat frames. And the first thing you do when you're calibrating is you create your masters. You create masters of your flats, your darks, and your bias. What you are doing when you're creating masters is you're increasing, you're combining lots and lots of flat frames, dark frames, and bias frames. How many? I take 25 flats, I have 50 darks, and I think I have 100 biases. They say you want more biases than darks, and flats, it kind of depends on a few things, but I'm comfortable at 25. The more is always better. Signal-to-noise ratio will always rise when you take more frames, so the more you can take, the better. You get the signal-to-noise ratio up in those frames so that you're not introducing noise into your light frames when you're finally calibrating. You have to have a sufficient signal-to-noise ratio built up, and even at that point you might be introducing noise into those frames, but it will improve the final images if you get it right. So you've created your masters. At this point, you want to subtract the master bias from all of the other master calibration frames and the individual lights. The bias frame is the read noise. The bias frame contains possibly all of the fixed pattern noise, or hopefully a good reading on the fixed pattern noise so you can take care of it right now, right off the bat. You remove it from your lights, your darks, and your flats. So keep that in mind. At this point, you're going to subtract the dark from the individual light frame. The dark pretty much holds the dark current. So think about what you've just done. You remove the bias from it. So you remove the pattern. You've removed the dark. You removed the read noise from it. The dark is going to remove the dark current from it. And those are basically your two sources of noise. Remember, the only fix for photon noise is time, and that's what you're getting just by exposing. And you basically remove those types of noise. Have you removed them perfectly? No, that would take an infinitely high signal-to-noise ratio on your master frames, which isn't really possible, but you can get pretty close. So you've subtracted the two sources of noise, but you still have to deal with the flat. And you know what the flat does. The flat fixes even uneven illumination, and it also fixes dust donuts. To do that, you actually divide by the flat. If you were to subtract the flat, the math doesn't work out. So you divide the light by the master flat. Now you've removed the bias from the master flat already. You've also removed the bias from the light. But think about what happens if you hadn't done that. You would actually be introducing the bias into the light at this point. You'd be creating a bigger problem for yourself at this point. And that's why we always push the importance of using bias frames when you're using flats. If you're not using flats, and I'm not recommending this, but if you're not using flats, you may not have to use bias. Bias do another thing. They also let you scale your dark current. They let you scale your dark frames. But if you're not using flats and you're not scaling your dark frames, you may not have to use bias. That said, I still suggest using all of your calibration frames. So you divide the light by the master flat, and pretty much your illumination is fixed. your noise is removed, and at this point you've got calibrated lights. You're ready to stack them. And we really had hoped to go into stacking, but this project was a massive undertaking, larger than I think we expected, and we didn't quite. I don't think we're going to quite get into a lot of that. But what I will show you, and I just like the way this is represented. This is a little bit of a flow chart coming from the Deep Sky Stacker website, and it shows you a little bit of the calibration math. And you can see there, the bias is first combined with itself, then subtracted from the dark flat. I didn't get into what dark flats are, but subtracted from the flat, then subtracted from the light, then that master dark, which has already had the applied bias, gets subtracted from the light. And you can see really how it works through. This is basically the workflow. This is what we do during calibration. When you come out of this, you have removed the primary sources of noise from your camera. You've removed a significant amount of them. Not all of it. We're doing something very difficult here. We're photographing really dim targets that are very far away, but you've removed a large source of it. So we've gone through some of the math, and just to kind of give you a primer, I think it would help you. Maybe I should have started with this, but I didn't. But how a CCD works at really the photon level. And a CCD is basically an array of MOS sites, metal oxide semiconductor capacitor sites. And these sites are basically a silicon substrate with silicon oxide grown on the surface. There's a layer of metal evenly deposited on the surface that when a charge field is applied to it, and this is my word, acts like a bunch of catcher's mitts. That charge field makes these photons strike the surface and immediately grab an electron and send it down into the well. The well is down at the bottom there, and that's really what holds the charge during the exposure. The entire thing acts as a capacitor, so it's holding the charge and just waiting through that exposure. Larger wells are better. Think about that. The more charge it can hold, the better. But I'm not going to get too far into that. At the end of the exposure, the wells actually pass the charge off to the side, and there's an amplifier sitting at the side. This is a little bit of the difference between CCDs and CMOS, or CCDs and DSLR cameras. CMOS sensors actually have the amplifier right at the well. I think they do that to get a little bit quicker of a read-off, possibly at the expense of some noise, but that's basically the real difference between the two. Well, I shouldn't say the real. As well, CCDs operate much more linearly, but in a sense, that's one of the primary differences. The amplifier at that point converts the charge into a voltage, and that voltage basically, and actually I'm not quite sure whether the gain is applied to the voltage. I think the gain is applied to the voltage at that point, but that voltage is pretty much at the ADC converted into a number. And the gain is important. The gain in a camera is important because they optimize the gain for the bit depth of the ADC so that you maximize the dynamic range in the camera. And the dynamic range in the camera is pretty much based off the size of the well and the amount of noise in the camera. And I think we might hear a little bit more about that. But as for now, that's pretty much the end of my side. And I'm going to pass it right over to Josh, who's going to take us a little bit further. But if anybody did have any questions just on my side, corrections, feel free to chime in. We'll take an intermission. And you can ask any questions now, or we'll move right on to Josh. Just getting my screen back. Any questions as of yet? And if not, I'm going to head right over to Josh. There you go, Josh.
Thanks, Adam. Appreciate it. So what I'm going to do is try to, I guess, more visually represent what Adam was talking about with a series of graphs. And I also have a spreadsheet put up that we can play around with some and actually look at how all of these numbers and values can affect what your final image is. So as Adam was saying, kind of through how CCD works, you know, you're collecting all this data through photons, and then once you finish collecting your image and shutter goes down, then you're going to read what's going on in there. In that process, you're going to generate noise from your read, and also the dark current is raising at the same time, and the part that you really worry about is the dark current noise. So one point that I'd like to make out that Adam was talking about with the read noise being squared is the reason that that is squared in this following equation is that, you know, the noise in a signal is the square root of the signal, and as you can see in this equation, the target signal, you have to take the square root of that, and the dark current, you have to take the square root of that to get the noise, the dark current noise and the target signal noise. But what you're putting into the equation in the denominator also is the read noise, and since it's already noise and not just the read current, which there is a read current, you have to square that since you're taking the square root of it also, so essentially it just becomes the read noise. So I think that is a fact that is worth pointing out. So I'm going to talk just a little bit about some of the CCD camera specifications that actually go into, you know, how your camera is impacted. So talking about the quantum efficiency, full well capacity, dark current, read noise, and gain. So the first thing that we're going to talk about is the actual quantum efficiency. And quantum efficiency basically, in a simplified world, is just what percent of the photons that actually strike your sensor get converted into signal. It's not like every single photon that hits your sensor is converted directly into signal, and a lot of our conversations about which camera do you want to get and why are you going to get it revolves around not only the read noise, which you want to be really low, but also the quantum efficiency as well as the size of the sensor. But the quantum efficiency is a big one. So this chart, and I'm not sure how well it shows up on here, what these specific cameras are, shows kind of the quantum efficiency line of each of the sensors. And the two that we'll kind of focus on in this presentation are the KAF 8300 and the ICX 694, the Sony chip. The reason that we'll focus on those is they're just kind of what a lot of the discussion has revolved around. But hopefully by the end of this presentation, you could also take the same information that we're talking about and apply it to any camera you're looking at and make a well-informed critical decision. So I'll point out the line with my arrow here that you can actually follow. The red line, which stands out pretty well, is the ICX 694, and it's known for being a very efficient camera. You can see over here at the 03 line, right around 500 nanometers, that it's converting 76% of the photons into signal, which is awesome. When you take that in comparison to the KAF 8300, you're living down more at around like 48%, somewhere around there. So not quite two for everyone, but certainly more than 150% of the efficiency of the KF 8300 is what the ICX 694 has. And then the same thing at some of these other lines we care about over at the Hydrogen Alpha and the S2. KF 8300 is quite a bit lower. Again, it's about 20% lower over on that side, and it stays that way throughout the sensor. There are trade-offs. It's not just that the ICX 694 is perfect, otherwise everyone would have it, and some of the issues are the size of the actual sensor. But there is no question that it's definitely a much more efficient sensor. So another thing that we can talk about when talking about cameras is the full well capacity. And basically what that is saying is how many photons can be registered on the pixel before it's full. And a good way to visualize that is a sensor is sort of like a big array of buckets that you put on the ground. And I think it's a pretty well proven analogy. Even lining the buckets up, there's little holes in between them, just like there are in a sensor. So not every water droplet that would go towards the ground would actually fall in a bucket, just like not every pixel that comes on your sensor would go into one of your wells. So going on into that full well capacity, at some point that bucket will fill up and it can't record any more information. And really, when you're imaging, there's two ways to image. One is to make the most of your dynamic range, and that means that you want your buckets to be filled just about to the very top, but not overfilling it, because at that point you've gotten all the dynamic range that you possibly can out of your image. However, especially when we're talking about narrowband imaging, you will have point sources of light like stars that are going to fill up quite a bit faster than the really faint regions in gassy nebula. And so a lot of times people will maybe take RGB stars to put in over their narrowband nebulas, or they might take separate length exposures to get the stars, or they might just be okay with white stars in their narrowband data. But so the second strategy would be just to expose as long as you can, or maybe an hour, maybe half an hour, and just live with the fact that you're losing information in some of the pixels in your camera. Usually in narrowband imaging, you're only going to lose information in very few of your pixels on the brighter stars. But when you're doing actual color imaging, it's a real problem. You can lose star colors if you expose too long. I think some people expose 10, maybe 15 minutes for their RGB filters, and at that point you're starting to push it, and you're definitely going to be saturating some of your stars and pushing them past the full well capacity. So just giving some of the specs of specific cameras, the KAF 8300 is 25,500, and the ICX 694 is around 12,000. Of course, both of these also will have a game built into them, which has an impact on it, and they also have different size pixels, which also has an impact on actually how many photons are hitting those pixels, which you'll see later on when we compare the performance of the two sensors. So, as I mentioned, one thing that's really interesting to understand and understand why calibration works is that when you are actually getting dark current and dark current noise, there are two things that are related to each other, and one can be calibrated out well, and dark current noise can't necessarily be calibrated out well. Dark current is just the buildup of charge in your sensor due to usually the heat in the sensor. So your noise is always going to be the square root of your actual count. So if you look at this graph, the thing that can be calibrated out pretty well and pretty easily is your dark current. As you can see, over time, it's just going to be linearly building up. This is an example of the KF 8300 chip. Actually starts just above 0 here, and that's 2/100ths of electron per second. And so when you calibrate your frames, you can take out that average, but it doesn't mean that you get rid of all of the noise. You're still going to have some noise in there, and the basically the uncertainty is in the noise, and that's this lower line down here, which is the dark current noise. So that cannot be calibrated out perfectly because there is uncertainty in where it lies, so you can't just get rid of that. So moving on into actually understanding how these guys interact, the dark current noise and the read noise in a camera, this graph shows two of the cameras, the ICX 694 and the KF 8300, and it also shows really powerfully why the read noise is a bear, why it's so much more difficult to deal with than the actual dark current. The data taken for both of these graphs is taken at -10 degrees centigrade Celsius. So we'll talk later on about how you can actually make that dark current noise graph grow more slowly so that it does not reach the read noise. However, a lot of our discussions on cloudy nights have been about longer and longer exposures. And the reason that you want to expose longer is because you want to get your signal up above this read noise. And I'll go to a next graph to show you why. It's actually your photon noise was what you really want to get well above your read noise. So this is the ICX694, and it's an example of an O3 stub that would be taken, in this case, with a 3 nanometer O3 Astrodome filter. And this data is extrapolated straight from information that I actually took. I'm going to pause for 1 second because I see a question from Glenn. Glenn is asking, the QE slide showed a line for ICX 694, 674, and what is the difference between them? I'll let somebody else correct me if I'm wrong. As far as I understand, the only difference is in the sensor size. The 694 is a little bit larger than the 674. I think that they have the same size pixels and same specs other than that. So anyways, getting back to this slide, what you see here is the photon noise in the purple, and according to quite a few sources, really the point that you want to get to in your images is to have your photon noise be somewhere around 3 times the level of your read noise. Or another way of looking at it is you want your read noise to be 5% of your noise in your image. And the way to get this is to expose longer. And the reason you want this is because what you really care about is your photon signal and the photon noise. And the only way to escape that really is to expose longer. So as you can see with this graph, the ICX694 does not have an issue with read noise at all, even out to 70-minute exposures. And if you extrapolate this graph out to almost 2 hours, your read noise just is not an issue. And this is at minus 10 degrees, so you could cool it even more. But to be honest, it's just not really necessary because your read noise will never overtake your dark current noise will never overtake your read noise, even out at 2 hours. And I've never heard of someone taking an image that long, although maybe we will someday, but right now we have not seen that. So going over to the KAF 8300, the story is not quite the same. As you can see, the read noise does start approaching the dark current noise does start approaching the read noise. And a lot of us are living right in this region right here at about an hour-long exposure. And at that point, the dark current noise actually becomes a bigger factor than the read noise. And this is for a single image right now. It's mitigated a little bit when you're actually stacking your images. It's a little bit of a different story, but it still becomes a considerable issue. So at this point, with the KAF 8300, if you expose to the point where the read noise is only 5% of your overall noise, you are still going to have quite a bit of noise from your actual dark current noise. So what we were going to talk about then is actually how you can take care of that, and that is in lowering the temperature of your sensor. As Adam mentioned earlier, a lot of times dark current will go down by half. The dark current will go down by half around 6 degrees. I think it's 5.7 to 6.1 degrees Celsius. And so, especially in the KAF chip, it's really important that you can actually cool the chip pretty far. The noise difference in the actual dark current noise is dramatic when you can do that. The hour-long exposure, when you can actually cool your sensor down to minus 30 degrees, the dark current noise is just a non-factor. It's sort of like the Sony. So you cannot get your read noise down like you can with the Sony. But you can get your dark current noise down to the point, if you have a better cooler, where it is not a big factor in your image. So moving on, we can just show you kind of the difference based on the equations that we were looking at earlier with the signal-to-noise ratio between the two chips. And over time, how you're actually getting more and more separation in the signal-noise ratio due to that read noise. The other thing that you can see is that your signal-to-noise ratio doesn't change up linearly over time with either sensor. Because you're dealing with the square root in the denominator, you are not building it directly over time. You get the most out of your image in the very beginning of it, and then the problem is you can't stop there because of the read noise. So you have to keep on exposing longer and longer, and you get a little bit of diminishing returns as you go longer. However, that can be dealt with somewhat with stacking. So once you get that good signal-to-noise ratio with a single sub, somewhere between usually 20 and 60 minutes on narrowband exposures, you can stack a handful of them. And once you start stacking them, then you can apply that same equation, replacing your subs. Replacing your time for the single exposure to subs overall. And you're going to build up the same way again. So your first few subs are going to make a big dramatic difference, and then as you keep building over time, you sort of get diminishing returns. But the cool thing is that this math actually does really work. And we were talking last night and saying, well, can we actually prove that that really works? It would be interesting to see. So I grabbed, went through my data and grabbed some of the information, and you can actually look at what the signal-to-noise ratio is in your mean signal over your standard deviation in a sub, and just showing the difference between one unstacked sub, which came out around 7.25, to the stacked sub, which came out at 17.4. So we talk what is good signal-to-noise ratio, and a lot of time it is a subjective thing. As with everything in our hobby, it is very subjective, and it's what you want to get out of it. However, there, I think, is sort of a minimum. We go through looking at everybody's pictures on the sites, and especially when you're looking at people who are trying to do narrowband imaging and they're first starting, and maybe they have a mount that's a little tough to get long exposures out of, and then they start processing their data. They're trying to process 15-minute subs, and it's a lot more difficult. It really is a lot more difficult to process them, and that's because their signal-to-noise ratio is usually starting out at 3 or 4 or somewhere around there, and their read noise is actually taking over the data. So you start trying to stretch it, and because that read noise is so dominant, your sky doesn't look like a sky, and it's very difficult to even smooth out because there is such a big dramatic variation in the data at that sky fog level that you can't stretch it much before it starts getting very jagged. I kind of like to think of the way the signal-noise ratio works as sort of a frothy sea of foam, I guess. And when you first start taking these exposures for a while, it's like the water's churning really, really badly, and you can barely tell where the surface of the water is. And as you go on a little bit longer and a little bit longer, the water's calming down, and it calms down some more, and you can start to see some areas where the water's almost smooth, and then areas where there's still kind of big ripples and stuff, and it's tough to tell where it's at. But if you wait long enough after churning that water up, eventually it becomes very smooth on the surface, and you can see the entire surface. And it's really a pretty good analogy to the way that images work, is that your signal starts really overwhelming all the noise, and you can actually see where the surface is. So that's sort of my end of the presentation for actually showing graphically how everything works. And I think that we could go into actually doing some questions and answers now and playing around with the graph and seeing how some of these statistics actually affect everything. I will let Adam step back in here, and we can start taking questions.
Thanks, Josh. Excuse me. Thanks, Josh.
Yeah.
Yeah, the graphs are really interesting. It kind of it makes me question some of my preconceived notions about dark current, but at the same time, it makes me, I don't know, I think cooling, and then it fixes it. So, but that said, interesting. I know Eric asked about the graphs, and if you have info on the Chi 1102M, and I think your graphs are mostly the 8300 and the ICX, but we might be able to plug in different specs if we can come up with them. Is that,
yeah, absolutely. I can see if I can bring that up right now.
all right. And if anybody has any questions that they want to throw out there, they're welcome to chime in. Glenn's asking, any way to compare the QE and/or noise of a DSLR to CCD?
Yes.
Go ahead.
The QE actually of DSLRs are not way lower than the QE of the CCDs, the KF 8300 anyways. The issue that you run into with the DSLR has more to do with the one-shot color and the microlensing, and that you're throwing a lot of data away. I think that for example, I had a Canon T3 that lived somewhere around maybe 5% lower than the KF 8300 across the board as an overall quantum efficiency, but then because of the Bayer array, you actually are losing so much of that information that it sort of artificially lowers the QE significantly.
And I think it's mostly hearsay, but I think modern DSLRs are somewhere between, if they were mono-fied, if the Bayer was removed, they'd be somewhere between 40 and 60% QE. That's how I've heard it. I think some people have used their cameras to kind of measure the flux and check it that way, but like I said, it's a bit of hearsay.
I can comment on that somewhat. So you have a little bit of a up and down on that, at least with a monofied one. When you monofy them, you actually are scraping off the micro lenses, and the micro lenses play a big part in actually focusing and capturing those photons that would be going between those buckets. So while you gain a lot of efficiency in the photons actually hitting, hitting every one of the pixels for every color that you would be shooting or every filter you'd be shooting, you lose a lot because of the micro lens. So you actually, from what I measured, you get somewhere between not quite as high as that 40 to 60%. I was getting like 30 to 50% based on that same thing. So,
we were discussing last night, actually, and there was a post on Cloudy Nights about the Kodak TrueSense 50,100 or 50,200, I think it is, the massive sensor they just released, and they put micro lenses on it, and it went from 25 PQE to about 60 PQE. So that goes to show you what micro lenses can do. They really work magic. Any other questions? There don't seem to be any questions. Josh, I don't see your. I see your dumbbell. I don't see your graph screen. If you're trying to show that to us.
I'm trying to pull up these specs on the 1100. Yeah, so I can actually share the graph while I'm looking those up, and if anybody wants to plug any other numbers into the graph, they can bring that up as well.
For the viewers out on YouTube or in the non-interactive session, you can post your questions on the Google page. I'm sorry, when I couldn't get you guys in, I forgot to activate the Q&A, so you don't have an easy way to post your questions. I'm going to go back to the Google page now and just check.
Adam?
Yes, go ahead.
Could you go into the exposure calculators that Starizona uses, CCDware uses, and how that math relates to what you just described, to what both you and Josh just described so well?
All right. Well, the calculators typically tell you how long of an exposure it's going to take till you've sufficiently pretty much the minimum exposure it's going to take to sufficiently overwhelm the read noise. And I'm not 100% certain as to how they work, but that's basically the point. You probably hear us saying you have to separate your histogram from the. Okay, no questions. Sorry, I was jumping around to see the questions. You guys hear you have to separate your histogram from the left side of the histogram, so to speak. That's basically what you're doing. You're separating your signal from your read noise. You're sufficiently separating it from the read noise where read noise won't be a factor. And
for those of you who haven't seen Star Arizona's calculator, and the other calculators like the one in SGP is calculated on the same basis. The numbers that Josh and Adam just gave us about how the read noise is a small percentage, 5% is a commonly accepted figure. That happens when your sky glow gets to a certain level. By sky glow, I mean the background brightness of the sky. And in different chips, different cameras, that value is different. On my QSI 583, it's at 1350, I think. On my SD7, it was 750. So if you put your cursor back in on the dark point of the sky in your image, you get a 750. You know that at that point on the SD7, you know that at that point about 5% of your picture is read noise, and at that point it's time to go on to the next exposure. Same thing if you put it in the background and it's at 1350. Well, let's say you've taken a minute exposure and you put your cursor on the background and find out that the ADU is something like 675 for the QSI 583. It's supposed to be at 1350 and it's linear, so 675 is 1/2 of 1350. So your 1 minute should have been 2 minutes to get to the level that you wanted it to be at. And that's how those calculators work, and it's all based just on the math that Josh and Adam just explained to us.
And I see Josh's graph, but one of the interesting things about those calculators is when you're shooting narrowband and you're doing those calculators on your images, sequence generator will pop up 2 hours. That's the optimum exposure for narrowband. And as Josh was saying, that is difficult. Not many people are doing that. So we're at the cusp there. We're at the cusp where we're separating ourselves from the read noise, but and we're always pushing it. So that's why we're all kind of doing the same thing, longer exposures. I hadn't heard of people doing hour exposures until the first few of us started doing them, and now it seems like a really good idea. Josh, are your graphs ready there? I see them. I don't know if you're plugging in the other figures.
Yeah, the only thing that I can't find is the actual dark current on it. I'm trying to find the specs online right now. Although I can actually show you right off the bat too here is if you keep the same telescope and go to this sensor, because of, and it's probably too small to see, because you're going to 9 micron pixels over the 5.4, you're actually getting your photon flux by comparing the ratio of the areas of those 2 pixels, and so the photon flux in each one of those pixels is dramatically larger, almost 4 times bigger. You can see over here my initial photon flux in my pixel was 0.18 or 0.17, and then 3 times bigger. And in the KI 1100M, it is actually almost 0.5, which makes a pretty big difference. As you can see, you're just getting a lot more signal to pixel in a hurry, and then you can actually see the difference in the signal to noise ratio is pretty dramatic as well. That builds up quite a bit faster. Now, that's only if you're actually holding everything else the same. but as soon as I can find the actual dark current noise, I can get the actual numbers on here as well.
On the SBIG site, they show it at -15 Celsius. It's
Okay.
0.5 electrons per pixel per second, -15. I don't know if they don't.
Okay.
I don't know if you have to compare it at -10 for it to make sense.
No, I can just show it on the noise characteristics. So that was 0.5. Does it say what the read noise is on there as well?
Read noise is 11 electrons RMS.
Okay. And I'm sorry, you said 0.5 or 0.05?
0.5, yeah, I thought that was seeming high, but yeah, 0.5.
Okay. So there you go with that. 0.5 is pretty high, and that's at -15, they said. So you can see here there's a pretty big, let me blow this up, it's probably easier to see if I make it a little bit larger to start with. Drag this out of the way. So yeah, you can see, I mean, the dark current noise actually takes over, you know, according to the math, it's really 0.5, 10 minutes into the exposure, which is not surprising because that would be 50 times, what, 5, and then, yeah, what, 50 times more noise than the KAF 8300. So you can see, you know, at that point, that actually makes a pretty big difference. And let's say, I guess pretty noisy for, you know, dark current for a camera.
And that is interesting.
Yeah, 0.5, yeah, 0.5 is really high. For comparison, the KAF 8300 is 0.02. So actually, it's 25 times higher. Sorry, and the Sony sensor is 0.002, which is 10 times less than the KAF 8300. So 250 times more dark current than the actual in the 1100M than the ICX 694.
And a higher starting read noise, too.
And a higher starting read noise. I see that Eric asked, isn't it true, you made a comment about star color and narrowband images. Isn't it true that star color has no meaning in narrowband images? Yes, it is, because as soon as you're using narrowband data, then you're not actually getting the true color of the stars. We've had quite a few debates about this all the time. However, you know, I think some of us fall in different camps. I know that a couple of the guys that we talk to a lot just like plain white narrowband stars, so they'll saturate all the stars to the point where they're white. I know some people like to actually try and maintain color in their stars, and so they'll get maybe bluer stars or a little purpler, yellower stars. And I think that that's more an aesthetic choice to try and actually retain color in them. And then what I typically like to do is actually replace my narrowband stars with RGB stars. And it's just a personal preference, and I think that sort of has to do with a lot of the strategy of how I actually process my narrowband images. You know, most of them have been bicolor to this point, and I try to process them in a manner that shows more red hues for the hydrogen alpha and blue hues for the oxygen, and keep it sort of natural looking as much as I can, and then actually put in the color stars, because, you know, usually no matter what you do, as Eric pointed out, your narrowband star colors aren't going to be accurate. So at that point, you know, I have no concern at all about how long I expose my narrowband subs. Yes, I use tone mapping to actually remove the stars, or at least, you know, minimize them as much as possible, and then I put back in RGB stars over top of them. Yeah, I mean, so because of that, you don't have to worry about how long you're exposing your narrowband subs for the sake of keeping star color. The only thing you might worry about in really bright images like the Dumbbell Nebula, or sometimes planetary nebulas are usually the brightest ones. If you expose for 90 minutes, you might actually be blowing out the core a little bit. Although I haven't run into that problem yet. I'm not sure if anyone else here has either. So.
I'm actually trying to help John Rista get in right now. If he's out there listening, you should be able to get in. I just sent you a new invite. Actually, Eric, I noticed he said he's running the STXL at -30. So that'll actually bend the dark current in that graph down pretty considerably.
So let's see. Yeah, let's see if we can figure that out. So if it's at -30, then the dark current should be instead of 0.5 should be, let's see, from -15. So that's almost 3 halves from that. So 0.25, then 0.125, and then 0.07-ish seems about right for that. So if we put that in, and then 0.07, sorry. And yep, there you go. So as you can see, it went from the dark current noise taking over right around 10 minutes into an exposure to taking over at about 30 minutes into the exposure. And even -40, we could try it again. So yeah, so I mean, you can see if we can drop it down just a little bit further, it would be down at 0.035. I guess even a little bit less than that because it's more than halving it, so about 0.02. And then you get back into the 8300 range. So that's about what you're looking at, is that if you can use the STXL at 1100 at -40, then it's, I guess, has similar dark current characteristics as the 8300 at -10 is what it seems like. So yeah, that's pretty cool.
That is interesting. The Sony sensors really are awesome in regards to performance, and I think everyone does the same thing. When they buy the 8300, they think about the Sony sensors and they say they're just not big enough, and they buy the 8300. But I don't know, the thought of going with the smaller telescope and a smaller sensor is very tempting these days. You get the same image scale and you get a little bit better QE. You could probably put it on a graph where the difference in aperture almost wouldn't, where the difference in aperture would make up for the quantum efficiency of the sensor and the performance of the sensor.
Yeah, I mean, I think this graph is the one that kind of really shows it, is that you're building up your signal to noise immediately, but it is sort of a trade-off in resolution. I think, I don't remember what, I think a lot of those guys who are using one of the nice combinations that you're seeing now is the TOC FSQ 106 and the ICX 694. I think they're running at about 2.2 arc seconds per pixel, somewhere around there. And I guess for a comparison with the 8300 chip and my 4-inch scope reduced down to about the same f ratio and focal length as that TOC, I'm getting 1.9 arc seconds a pixel. So I think that's about sort of the trade-off you're getting there. But then it's a field of view question.
Yeah. I see John's in the room, so I don't know if he caught the earlier presentation, but thanks for your input earlier on. This topic actually took a lot of prep work, so I'm glad we had the help.
Geez, that took a very long time to connect.
Yeah. We actually had issues right from the start, so go figure.
Oh, okay. Yeah, I lost my internet for a while there, and anyways, I guess I missed the presentation, so I hope it went well.
It did. You can check it on YouTube, but really, I think we might get some interesting stuff out of the discussion. I'm still curious, and I have to throw this question out for the discussion, that dark current, dark current noise, or the dark noise, is gonna grow no matter how many exposures you take. It's gonna grow over time, and the read noise is gonna stay constant over time. But the read noise is gonna integrate. Is the dark current gonna integrate the same way? I just see read noise as being such a greater barrier, even though the dark current is surpassing the read noise at a certain point at, say, 50 minutes. Well, what are your thoughts on that?
And just to be clear, it's the dark current noise, not the dark current itself.
Right.
Yeah, I mean, parts of read noise will integrate, and hot pixels will integrate. Any fixed banding you have will integrate, and dark current, is gonna of your hot pixels. So over time, I think both dark current and read noise have a component that will become reinforced the more you integrate. If that makes sense.
Yeah. So it's not just
one or the other is worse than the other. I think eventually, once dark current kind of gets big enough, it is going to become just as much a problem as read noise, because it still has a fixed component, those hot pixels.
Mm-hmm. And we haven't gone into dithering and that's impact, but even I think mathematically it's hard to show how dithering really impacts it. I don't know.
Yeah, I'm not sure exactly how to mathematically describe dithering. I haven't tried that yet.
Yeah, even the initial topic that stimulated this was how does the SNR ratio carry through different stacking algorithms?
Right.
Which will be a whole other presentation altogether.
Right.
Yeah.
Which is what I found out when I started actually looking at it, because you also want to include stacking algorithms in there, and then to some extent the difference, there's a lot of discussion between, are you calibrating with only bias frames or with dark frames as well, and why that makes a difference. So I think that can all be lumped into a whole other presentation.
Well, I'm sure we'll have more of those. We're continuing to get lots of viewers. We're filled up in the room today. We have between 6 and 8 viewers in the outside broadcast, just kind of peeking in. So pretty good response today. Anyone else have any specific questions on CCDs or calibration or anything we've discussed today or anything related? Anything unrelated?
I think it would also be nice, maybe while we have a handful of people in the room asking for further topics too.
Yeah, I was planning on that, and this actually goes out to the live viewers too. Anyone has any topics in mind for future broadcasts? Lay them out here. Our mount session is actually very well viewed. Lots of interest in the room immediately, and on YouTube following up. And we still have some mounts to cover. We haven't gone over a few of them. Paramount, I think we're going to try and have Mike Miller go over it during his live broadcast. But we also want to go over some of the more boutique brands, the Avalon. I know there's been some interest in. And there were a few other mounts we missed. So if we haven't gone over it and you have it and you can explain it, feel free to offer, or just drop me a PM and we'll try and get you in. Any other ideas for topics? Anything you guys want to hear about? I'd like to go over a topic on OTAs, and I'm sure we could cover a bunch of different OTAs and styles all in one session. What's good for imaging? What's good for imaging for the price? We haven't done much hardware, so that could be a good one. Even CCD cameras at the same time, go through all the CCDs, which might be a great follow-up to this.
Yeah, I see Glenn just asked anything to watch out for in around $2,000 cameras with the ICX 674. I see 3 brands offering that. The ones I know of are QSI and ATIC and QHY. So I'm not sure.
There's also a Starlight Express.
That's right, and Starlight Express. And there might even be more, but those are the ones I know of. I don't know. I mean, and as Adam mentioned, I think it's worth a whole discussion on CCD cameras, but a lot goes into if you're going to buy one of those, if it's going to be mono, what size filters do you need for that sensor? You know, some of the cameras that come with that sensor still only offer 36 millimeter sensor or 36 millimeter filter wheels, which could double the cost of your filters. Is an off-axis guider included or not? And if it's not, what kind of adapters and accessories do you need to put your off-axis guider in there, and then on top of it, how much does it cool? Like we saw, and it could be an issue, probably not with the Sony sensor, but at least if it's regulated cooling or not. So.
All right. Well, if there aren't many other topics and nobody has any suggestions for future presentations, bring up anything unrelated now, or else I'll probably call it a night pretty soon. Okay, well, thanks for coming. If you're out in YouTube, I'm going to stop the live broadcast now. But before I stop it, I just want to thank everyone, because this did take a bit more effort than I think we initially planned. It was a cool time. It got down to the nuts and bolts of it. We realized how important it was to get it right. So thanks to everyone that helped, including John and David and Jim and Mad Ratter and pretty much everybody. Yeah, Eric, see you on Astrobin. I just saw. I think you overtook me. So congrats. Yeah, and thanks everyone out there for coming on.